Yeah, hello together and welcome to our lecture series on climate protection. Today our guest is online, Albana Illo. Albana Illo is assigned to the Faculty of Electrical Engineering and Information Technology as an Associate Professor of Electrical Power Distribution Systems since 2021. She worked for Siemens Austria as a principal key expert consultant for electric energy supply systems, and then she returned to TU Vienna in 2013 and wrote her dissertation, Link, Based Holistic Architecture for Future Power Systems in 2020. She is credited with the Link paradigm and the holistic solutions for smart grids derived from it, which enables the decarbonization of the economy and the democratization of the electricity industry, and for which she also received the 50 Most Impactful Green Leaders Award. Moreover, she is the author of 3 international patents. Well, all this work is the basis of her presentation of today with the title Energy System of Systems, the way to accomplish the energy transition.
Mr. Pfluger, many thanks for the invitation to give the lecture Energy System of Systems, the way to accomplish the energy transition in the Ring lectures. So I'm Albana Illo from Technical University of Vienna, a power engineer. And then let me begin fast because we just have lost some minutes. So what we are going to discuss today, we are going to talk about the energy transition. We will have a short overview of the energy systems. We'll talk about smart grids and the holistic approach, link the energies, and we will talk a little bit more for the energy system of system, and then conclusions and outlook. So let's begin with the energy transition. What is the energy transition? Or in German, we are using the word Energiewende. The energy transition consists of transition to an energy system with low greenhouse gas emissions. Renewables replace fossil fuel generation and nuclear in some countries. Increase the integration of international electricity markets. It is staying for a better integration of transmission and distribution constraints in electricity markets. It is staying for sector coupling. That means a coupling between the heating, transport, and the industry, and for the industry electrification, and for more decentralization and the ownership of the power sector. Here we talk almost for the democratization of the power system. What is an energy system? Just to begin the lecture with some definition, the energy system is composed of multiple components that interact to produce, convert, and deliver energy for a specific end use. The energy systems can be analyzed through an engineering and economic and ecologic perspective. What we see here, we have almost 3 main blocks: the energy resources, and because the resources are normally situated far away from the demand, we need the energy vector, or we need the energy flow that can be finally used from the end customers. Through all the processes, there are created waste, and all this stuff, all the energy sectors are in a continuing interaction with the natural environment. Let's begin with the energy resources. What is the decarbonization process? It is the process of reducing the carbon content of something, and in the context of climate change, it primarily focuses on reducing the CO2 emissions. We are talking also for the net zero, and what does it mean, this one? That means that a country takes so much CO2 out of the atmosphere as it puts in. Here we have just an overview of different resources, and how can be they are classified according to the CO2 emissions. So CO2 free primary resources can be classified in two main areas, with a less environment impact and with a large or big environment impact. And with a less environment impact, there is the solar, wind, water, geothermal, hydrogen energies, resources. And with a very big impact on environment, there is the nuclear energy resources. For the net zero, then we can talk about the biomass, the biogas, or synthetic gas. And then we have the other energy sources, which are very polluted with CO2, and this is coal, oil, natural gas. There are the fossil energy resources. Energy can be completely defossilized, for example, through the renewable wind, solar power, and synthetic gas, biogas, and biomass. That means if we are talking exactly in the case of the energy, so we can talk more for the defossilization than for the decarbonization. So let's go back. So we talk and we mentioned the energy resources. Let's go to the next step, to the energy vector. What is this one? To talk for the what is the energy vector, which implies the flow of the energy. The pathway from the primary resource to the final use highlights several needs. First of all, the primary resource is generally available in a different place comparing with the energy demand. This implies, in the near totality of cases, the need of energy transportation. Moreover, the need of continuously and instantly satisfying the energy demand makes necessary a storage. And then we will use in this lecture the term energy vector, which is nothing else than a tool that allows the transport and or storage of energy. That means when we are talking, we will talk for energy vector, then we have to think that there is a transportation possibility like lines or pipelines, lines for the electricity, or pipelines, for example, for the gas energy. And also we have a storage behind this one. Let's continue then. What is an energy vector? Allows to transfer in space and time a quantity of energy. It allows to make the energy available for use at a distance of time and space from the source, intended as the point of availability of the primary resource in nature. The main energy vectors currently in use are the fossil fuels, oil and the derivatives, natural gas and derivatives, coal and derivatives, the electricity, hydrogen and other synthetic fuels, heat exchanging fluids. These vectors allow the transportation of different forms of energy, and thus the fossil fuels are using the chemical energy, the electricity, it is using the electrical energy, the heat exchanging fluids, it's using the thermal energy, and the hydrogen and other synthetic fuels are using the chemical energy. And then we have the last big block is the final use, and these are the end consumers. Which have, if we will try to defossilize the energy sector or to decarbonize, for example, the end consumers will need to change their appliances. For example, if we are going to step to hydrogen, then they have to change all gas appliances, which normally it is too slow to counteract the climate change. Let's go to a short overview of energy systems, of the energy systems. So we are talking for the decarbonization of the economy and how it is classified, the economy of a country, of a nation. It is normally classified in three main sectors. In the primary sectors, where the economy is based almost in extracting, harvesting products from the earth, such as raw materials and basic foods. Then we have the secondary sector of the economy, which produces finished goods from the raw materials extracted by the primary economy. And this is for us a very important sector, because in this sector are included also the energy utilities. In the tertiary sector of the economy, it is also known with the name of the service industry. So if we are beginning with the economy, so we have the economy is classified in the primary sector, secondary sector, and tertiary sector. And the energy utilities are situated in the secondary sectors. And each of the energy utilities, they are operating a system, an energy system. For example, one of the oldest energy system is the gas system. And if we see just a brief history, the first gas systems or pipes are constructed 500 years before Christus in China. And then we have the commercialization of the natural gas first in Britain at around 1785, and continue then in US in 1816, and so on. And we have now in Europe, in Germany, in the mid of 19th century, it is noticed the commercialization of the gas industry, and then furthermore, then in also in Wien, Hamburg, in 1869. And if we are looking today, we see that there are a lot of pipelines which are constructing through the Europe, just supplying gas everywhere. And why I'm mentioning this one here, because it seems that the vector of the gas system, it is available, it is here and very extended in Europe. The other point, it are the end users that we discussed, and then there are a lot of end users which are using gas, like gas stoves, gas heater, gas condensing boiler, and also gas turbines in the power plants. That means if we are coming back, then we see that the gas system has a vector which is very extended nowadays. And when also the end users, that means we have the customers that have a lot of appliances that are using the gas energy. Another energy system is heating and cooling system. Just go also brief there. So we are talking in this case for district heating systems. They are normally demand driven. That means that the heat supplier reacts to the demand from the consumers. And if we are going fast, we can distinguish 4 generations on the development of the heating system. So it is the first generation beginning at 1880s in US. And then we have the second generation that was developed from 1930s and until 1917s, where they burned coal and oil, and the energy was transmitted through pressurized hot water at the heat carrier. And then we have the third generation, which was developed 1970s, using prefabricated, pre-insulated pipes, which are directly buried into the ground and operates with lower temperature, usually below 100 degrees. And we are at the fourth generation, which is being developed. It is designed to combat climate change and integrate high shares of variable renewable energy into the district heating by providing high flexibility to the electricity system, which we need in the presence of the renewable energy resources. And here we have an overview of a district heating system. We have a vector which exists nowadays, and we have also the end users. So if we are coming, so normally we are talking for district, for heating and cooling systems, and the district cooling system are not that old. The first one has been introduced in US in the late 19th century, and it was much more than developed until 1960s. From this one here, in the second generation, the district cooling system introduced in Hartford in US was based in large compression chillers and cold water as distribution fluid. The first major European district cooling system was established in 1967 in France. And then we have the third generation, which constitutes of a more diversified cold supply based on absorption chillers, compression chillers, and so on. And then and the early initiative was the formation of the climate space system Paris City Center 1991. And the fourth generation have emerged in 2000 and 2010s when the decarbonization of the cooling became increasingly important. That means also this is just an overview for the district cooling system, and also in this case we have a vector, we have also an end user which are using this one here. So we have a vector and end user. The third one, it is a hydrogen. Many people are talking nowadays for hydrogen, and with this we'll realize the decarbonization of the economy, not only the of the energy, not only the defossilization. And the history of hydrogen is very new. The beginning, it is 1918 in 1800, where the English scientist Nicholson and Sir Carlisle discovered that we know discovered the electrolyzers. And later on, they also discovered the fuel cell effect in 1839. The hydrogen has been used in the chemical and other process industry on a large scale for decades. And in 1959, the English engineer Bacon built the first practical 5 kilowatt hydrogen oxygen fuel cell that was used to generate heat and electricity and provide water. And this is the first commercial use of the hydrogen. But currently, what is the situation? Power generation basis, from the point of view of the power generation, electricity power generation, more or less no use is of hydrogen for it. About 0.2% on the cases will be used to produce electricity. When from the point of view of the pipe infrastructure, worldwide, there are currently more than 4,500 kilometers of pipelines of hydrogen, and in Europe, we can find almost 1,600 kilometers. And it is not comparable with the extension of the pipe system in the gas with 100,000 kilometers. And there are a lot of pipes also in construction. The gas devices of residential users do not work with hydrogen, and this is one of the biggest issues that it is there, because it needs a very long time until end user has changed their appliances that should be also produced to work with hydrogen. Another point, and the fact is that the hydrogen, the natural gas, can take in only 10% of hydrogen, or the end appliances, the end devices, we cannot work. And we are talking for hydrogen for a future vision in 2050, where the water will replace fossil fuels as the primary resource for hydrogen. So there is a very long vision. For that reason, the hydrogen system here, it is presented in dashed lines, because the vector, neither vector nor the end user have the appliances to use the hydrogen. And the last it is the electricity system. So when we are talking for the power system, and we are seeing the vision of the ENTSOE, that is Electrical Network Transmission System Operator Electricity, their vision, it is that the future power system in Europe will be a system of systems which will need strong cooperation between transmission and distribution and amongst different energy systems. All operators will be key enablers and facilitators to make this future energy system work. And when we are talking for energy system of systems, so we have it is a possibility to integrate the gas system, the thermal and electricity system, and they have to work in integrated fashion to explore synergies and optimize the flexibility of using renewable energy for a carbon neutral energy supply. So electricity system is a central system for the um, for the integration of the renewable energy, for the decarbonization of the energy system. So if we are having just a very short overview of the history of the development of the electricity systems, then there are three areas that can be identified. It is the legacy distributed power area, 1880s from 1910, which is characterized by small distributed power plants which provided electricity to local customers through DC power lines. Then we have the central station power area from 1910 to 1990s, characterized by large power plants which supplied power to the distant load centers through AC power lines. And then we have the integrated, that is the new era, the integrated energy systems era, beginning with 2000, characterized by the re-rise of the small and very small distributed power plants. The transition of the third area is ongoing and can be unfolded in two phases. In the first phase, the electricity industry liberalization, which began in 1986, implied planned changes forced from political decisions. It was Margaret Thatcher which decided first to liberalize the energy sector. The liberalization put the old order completely in question. The market rules overcome the technical. Several blackouts and electricity crises happened at this time. And so, for example, we can mention the electricity crisis in California 2000 and 2001. And the second transition phase, it is, so let me go back. It is the smart grids, where we are now, and this is the second phase of the third area of the integrated energy system. So let's go to the smart grids and the holistic approach link. What are smart grids? And this is a big issue nowadays. We have in different countries different definition of the smart grids, which are changing, evaluating from year to year. But it is a definition of the electrical of EPRI, it is Electric Power Research Institute in US, which has done, they have done a holistic definition of the smart grids, which refers to a modernization of the electricity delivery system to monitor, so it monitors, protect, and automatically optimizes the operation of its interconnected elements from the central and distributed generators through the high voltage transmission and distribution grids up to the industrial users and to the end users and their thermostats, electrical vehicles, and so on. What should do a smart grid? The smart grid should provide quality, reliability, and efficiency by dynamic optimization, accommodate all generation and storage options regardless of technology and size, enable electricity market to flourish, and motivate consumers to actively participate in operation of the grid. That means to realize the democratization of energy sector, the power system. So here we have the electricity power system, then, which has a factor. We have the old Europe and the old in the world. We have the lines, the electricity lines that are extended everywhere, and we have also the end users which are using every day in our households, and also our laptops are working now with electricity. Then the end users that are used are sitting in different sectors of the economy. All end users of the primary sector, of the end users of the gas system, and also the end users of heat and cooling. That means electricity is used also in the agriculture, but also for the services. That means it is everywhere. Then when we are talking for the cross vector sector coupling, that means we have to couple, to integrate the vectors of the energy systems, which are lines and storage that are there. And then we are talking also for the end user sector coupling. That means the coupling of the sectors in the level of the end users. So from here and through the through the system integration process, we so it can be derived the energy system of systems. It can be, yes. So let's continue now with the electricity or power systems. To have an overview, a better overview of the electricity or power systems, so I would like to make an analogy between the human body and the power systems to have a better overview of this one here. So if we have a human being, so the basis, it is the skeleton, and over the skeleton are set up the muscles that the skeleton may move. For this one here, it is needed a nerve systems, and then we have also the brain. Let's break down then to the power system. What is this one? Under the skeleton has to be understood the structure of the electricity production facilities, the wires, the transformers, and so on. And this is the basis, the hardware of the power systems. First of all, should exist this one here, and then we can begin and talk then for the power system. Then the second one are the muscles. In the power system, we have to talk for the control units. They are considered as muscles, which, for example, can close and open the water or gas injectors to increase or decrease electricity production, and so on. And for the communication, the system nerves, it is including the measurements, the receptors, and that carries, and these receptors, and also the communication system that carries information or instruction from the brain to the muscles. While the brain, it is the control center of the energy systems or the power system, which controls and operates power system reliably and safely. Just to have an overview, then if we have a change in the structure itself, then it means that we will talk on a new architecture on this one. And here we have an overview of the electricity grid, just having so we have here, normally we have a transmission level to transmit the energy from point A to B, because the sources are far away, the energy sources are normally far away from the demand centers, so we need a very high voltage level lines. Then we have the distribution level with medium, which have two levels, the medium voltage level and the low voltage level. And then we have also the customer plants, which are the houses where we are using our devices. That means that this is the vector. In each of them are connected now electricity storage, to know it, and also the different power plants. What is the smart grid scope? What is the difference between the smart grid and the power system, the traditional power system? And this is coming and is derived from the definition of EPRI, which is included not only the high voltage transmission grid or the central distributed generation, high voltage transmission grid and distribution, but also the thermostats and vehicles and appliances and other household devices. And if we are trying to see it here, this is the traditional power system, high voltage grid, medium voltage grid, low voltage grid, where the houses themselves are not included in the scope of power system. That means the utilities do not operate or use the appliances in the households. They are responsible only for this part. And if we are coming to smart grids, then we see that also the households and the appliances are included in the definition of smart grids, and the number of the distributed generation, it is increased. That means we have this one here, a change in the structure of the power system, which is the skeleton of the system. Let's go a little bit and say, okay, if we have one tree, only one tree, and we are trying to cut it, it will not have a big impact in the nature. But also, if we have only two trees, it will not have any big impact. In a forest, we have thousands of trees, and the impact, okay, is larger than the other ones, but not that big. But then we have millions of trees in Amazonas, and if we are trying to destroy the Amazonas, we will have an impact in climate. That means that quantitative changes may lead to qualitative changes in other areas. That means also in power system, in the case we are at the beginning, we just included only one photovoltaic, only in the system, nothing will change. Also two. But if we are trying to install photovoltaic in each rooftop, then we have a big impact, qualitative impact in power system themselves, because its structure is changed. And for this one here, and here we are coming in the modern system architecture, which is necessary just to have an overview on it. And from this one here, from the modern system architecting, we learn that whatever the type of the system, one of the fundamental principles of system architecting is reasoning according to an architectural paradigm, where a paradigm is a symbolic model or diagram that makes it easy for us to understand the essential characteristic of a process. Normally, our architectural system consists only of timeless patterns, and the patterns themselves are characterized from unique and independent elements. This is very important. So there is no time to analyze here, but for example, why microgrids are not giving any solution, although the concept was introduced in 2003 for the first time. So there are more than 20 years development, and then we have no results. Exactly, we need a pattern, we need a paradigm, which has to fulfill this condition. The parameters or the elements of the patterns should be unique and independent elements. The architecture itself, if a system is a global model consisting of the structure itself, properties of various elements involved, relationships between various elements, behaviors and dynamics, and multiple views of the system, complementary and consistent. That means when we are talking for architecture, we have to treat all these issues. So we have a change in the structure of the power system itself. We have seen with the increasing of the decentralized, of the distributed generation, a lot of photovoltaics on the rooftops, for example. So we want to use in an intelligent way also the electrical devices. That means we have a change in the structure of the power system itself. And we would like to analyze this one here. Many people are talking, oh, this is very complicated, this is so time, and. But there are, if we are just looking and taking examples from the nature, then we have to think, and we can just learn, or we can use the fractals as a principle exactly to design the architecture, the new architecture of power systems, where with the fractals help to go from simplicity leads to complexity, and our goal is to go from complexity to simplicity. And we have to find what is the smart grid fractal pattern. What is a pattern? So we think on fractals in a simplistic but still useful way as geometric figures which repeat themselves at progressively smaller scales. With a fractal, there is often a self-symmetry or approximately self-symmetry. And here, because we would like to just to have a solution where we can use also standardization, because it should be also payable from everybody, the electricity. So let's go to the fractality of power system, fractality structure, and then we have a branching structure in the fractality of the trees. And if we go to the smart grids, does the smart grids have a fractal structure? If we see it in this way, probably not. But if we try to change the position of the tree, then we will see, aha, probably we have a branch fractal nature also in the power systems. So let's go further. One of the most important findings in the work on identifying the link paradigm, or the paradigm of the systems, it was just considering the customer plans. We have, if we are going here, what we have here, we have just a one family house. For example, here we have the connection, the low voltage customer plant connection to the low voltage grids, and in the house we have a lot of cabling which are creating a radial grid within the house itself. Because up to now we're treating the households or the houses like black boxes. If we try to go inside, then we will see that we have also in the houses themselves radial structures, the same as the radial structure is in the distribution grid in low voltage. And at the end of the, for example, of these lines of radial structure are connected different consuming device. So we have a very similarity in the construction, and here it is also a producer. We have a producer, and we have also storages in the case of electrical cars, or if in many cases are installed photovoltaics with storages and so on. And this is one of the base finding of this work, including and treating also this one, just to find the fractals. Good. If we go to the smart grid structure, so always the fractal, it is based on the fractal itself. So we have to find the fractal pattern. What is the grid? The grid itself is a construction that provides the connections among the points of power production and consumptions. It consists of wires, transformers, and reactive power devices. And if we see, we have different, we have, for example, I have here token here in in this case, the wires are very long. For example, for the transmission grids, then this is normally a cable used in the medium voltage grid, and these are in the low voltage grid, and this is kind of cable are used in the households, and this is in the devices inside. And here we have lines that are long, let's say up to 6,000 kilometers. If we are going to low voltage, we go up to 100 kilometers. In medium voltage, if we go to low voltage, in Europe, we have the longest low voltage grid, 2 kilometers. If we go inside the house, we have, let's say, up to 100 meters, the longest one. And if we go to the equipments in the wash machine and so on, probably we have some tens of meters if we are trying to measure the length. That means we have, and this is fulfilling one of the requirements of the fractals, it is repeating in a smaller and smaller size. The same we can say for the transformers, and these which are in different voltage level, for the reactive devices, reactive power devices, which also up to these are condensers used in the high voltage grids, and these are, for example, in equipment level. That means we have different sizes. And then we have another category, active power appliances, are appliances that mainly produce, consume, or store active power. And these are the rotating machine, that is a generator in 6.3 kilovolt. And here we have the photovoltaics, for example, and here we have the batteries, because all of this one here are producing active power. By definition now, so we have to find the fractal pattern. The fractal pattern of smart grids consists of electrical appliances designed for a predefined level. And then we notice them with ellipse, and these are the grid elements and the active power appliances, and electrical, it was ELA for electrical appliances here. And then if we are making the analysis here, we'll see, okay, we can create electrical, this is the basis, And then from here, we can derive the different fractal levels. And this is the high voltage grid. This is the grid itself. And then we have the big power plants, water power plants. And this is a pump water power plant, which is a storage. That means there is a connected the producer and the storage. And this is the grid. The same we can do it for the medium voltage. This is the level 2, the level 3 low voltage. And if we go in the house itself, we have the customer plant grid within the house. Then we have the producers with photovoltaic, cooling, heating. We have also that can be used like a storage type of storage, and the batteries of the cars. And then in the level 5, here we are the equipments. For example, the wash machine inside. If we are trying now, how can we create then the fractal pattern? Just where we will do an analogy with power system itself. What we have in the power system different zones. We have here the high voltage zone, the high voltage grid it is. Then we have the medium voltage grid. We have the low voltage grid. We have the customer plant zones. The number of the main elements are included within these zones are shown in this table here. These are real numbers. For example, for Austria, we have a real number for a real power system. In the normally there is a high voltage zone. Only one high voltage zone in Austria, for example, which is operated from APG, Austria Power Grid. Then we have 300 medium voltage zones. Then we have almost 100,000 low voltage zone and 4 million customer plants. And when we are coming to the devices, here we have done the assumption that each house has only 10 devices, which is not true. And then we are trying to using scaling factors because we would like to present this fractal pattern in so in the slide. Then we have used the different scaling factors, and then we found out that the number of the ELAs of the fractal pattern, it is 1 for the high voltage grid, and we have the level 1. The 6 for the second level, 18 for the level 3, 72 and 720. When we see here the behavior, here we have in this axis, in x-axis, the high voltage, medium voltage, low voltage zones and the devices of a real system. And here it is the number of zones. And if we are going in the presentation of the fractals, we have the different fractal levels, and we see and the number of the ELA patterns. Then we will see here that we have the same behavior. They are both exponential. Based on this one here, so it is constructing the set of the fractal set of smart grids. And here it is a territorium. It is shown in a rectangular. Let's say it is Austria. And here we have one high voltage zone, high voltage ELA. Then we have 6 medium voltage zones calculated before. Then we have 3 in each of them 3 low voltage zones, and then the houses themselves. And then we can go on this too, then in the devices within the houses. And this is the fractal set of smart grids. Then we will have everywhere the same situation. Now we have to go to the architecture itself, and then we have to find the elements. The one of the picker was the structure. Then we need the elements. What are the elements? For this one here, we have to define a paradigm. And for this one here, well, let's think on a technical system which has normally 3 major systems: has the hardware, has the automation, has also the communication. And then here for the hardware, we will take the fractal pattern that we identified. Then for the automation are the control schemes, and the communication is the interface. Based on this one here, it is derived the so-called link paradigm, which is basis then. Link paradigm is a defined set of one or more electrical appliances, grid part, storage or producer device, the controlling scheme, and the interface. For this one, so we need a holistic technical model to derive then the architecture, and this is the holistic model of power system. We have on the two axes, the horizontal axis, they are presented the transmission grid, and the horizontal axis, they are presented the medium voltage, low voltage, and the households themselves. And here it is the model. The energy supply chain net is a holistic technical model for power systems that consists of a set of automated power grids intended for chain links which fit one to another to establish a flexible and reliable electrical connection. Each individual or a link bundle operates autonomously and have contractual arrangements with other relevant boundary links or link bundles. Based on this one here, and to define then the elements of the architecture, it is done here analysis of the energy carriers and the means of transport used in the conversion process. So here we have the different various energy carriers. Then we have coupling components like generators, PFO cells. Then, and these are the producers, which are characterized with one directional energy conversion to electricity. Then we have the grid, energy transportation, and the storage, bidirectional or further energy conversion up to the consumption and the end phase. That means that we define here three elements of the architecture, and how we'll look this one here. So we have the producer, storage. All these elements are in the structure of the pattern ELA that we define it, and then we have also the control schemes. The second element was the control schemes, and so the control, the most popular control strategies in power system are the local control system. Then we have the primary control, and what it is very important is the so-called secondary control, which is set up normally in a control area. I'm not going in the details of the automation controls. So based on this one here, from the link paradigm, which was electrical appliances, the fractal pattern, the control scheme interface, the architecture element are the producer link, and here are included only the producer using the primary control and interface. Then we have the storage link and the grid, which here the difference with the other one is here we have a secondary control which is set in an area and has to coordinate with the other elements. So if we go to the architecture itself, it looks thus in this way. Here it is the high voltage grid, the medium voltage grid, the low voltage grid, and also the customer plants. And then in each of them are connected storage appliances in all voltage levels, in all fractal levels, and also producer. And if we are seeing this one here, thanks of fractality, we had there the same structure everywhere. That means we can put them all together. And what it is important we discussed, it is we have also to consider also the market, and this is the holistic link-based architecture of smart power system and electricity market. What it is important, because many people are talking for automation, for digitalization nowadays, the core of this link-based holistic architecture is the automation, because we have seen it is also in the definition of the paradigm itself. This is the core, and then it is digitalization. Without the automation, no digitalization is possible. Another very important point, it is the market. This is the actual market nowadays. Everybody of us have experienced the very high prices of the electricity that we had and how it works nowadays. This is the market, the electricity market, which is based on the merit order mechanism. And here are bidding and asking the big producers and big consumers. And then we have the energy suppliers, which also are bidding and asking. The TSO, it is enabling this electricity market. Then the small producers, small consumers or prosumers, that are us, have then to deal with the energy suppliers normally, which are setting the prices based on the contracts. And this structure of the market do not help in further integration of the renewable energy resources, based then on the fractal models. We have seen that the technical model of power system has a T form, and it is also the link solution proposing also a T structure of the market. And then we have here the national, international market, the regional market, and the local market, which will enable also the small producer and to trade the electricity. And here it is defined the average trading volume as a fractal parameter. And here we have overview of the market structure now derived from the fractal links level. And we have here the international national structure of the market, wholesale market transmission or wholesale market distribution, but also a local market for the energy communities. Very interesting is that all participants are the same. So we have here storage prosumers, which both behave similar in the market in all of these levels. So we have here, we have kept the fractal features. What it is important also, the mechanisms used there are it is also the merit order. It is used everywhere in all of these levels. In the international national market, it is used the merit order, but also in the regional and also in the local community. That means we have the similarity in all this kind of markets, which is one of the features of the fractality that is respected on this one. Now, if we would like to have an overview then of the architecture, what we see how it looks, this one here. Based on the fractality, we have here in the middle the different grids, a high voltage, medium voltage grid, low voltage grid links. And when we are talking for grid links, then we will understand behind the structure itself, the grid itself, the secondary control, but also the interfaces that can communicate with the other elements. And they are put, because of the similarity, we can put them all together. So it's helping a lot then, for example, in showing the process of demand response, which is not included, and because of the time is very short for this lecture. Then we have on the left side, we have the producer link. What are behind here are all electricity producer, the power plants, hydropower plants, or the wind or solar, regardless of technology and of the size. And they have because the paradigm itself has also the automation. And then we have the primary control behind, and also the interface that they communicate with each other. On the right side, we have the storages. Also, storages exist. This storage is not new. The water the pumped water power plants, hydropower plants are very old. That means the concept of storage was used in power systems. But now we have, because with the development of the technology, we can storage the electricity in different ways. And then we have here, for example, presented cooling and heating, which is going then in the direction of the sector coupling. Or also the hydrogen. Normally we want to produce green hydrogen. That means from the renewable energy resources. In the case we have a surplus production in the power system. What it is else, it is also, these are the households, which also have also inside the same structure at the whole power system. They are presented separately because they are organized in the energy communities. In this case, and this is a result of the Interact project, and who would like to know more just can go to this link. And then we have the market, and here we have the international market with average trading volume of terawatt hours. And then we have the regional market, which is facilitated by the DSOs. And then we have also the local market, which is should be normally facilitated by energy communities, because we are talking and we are thought, okay, one of the issues of the energy transition is the democratization of the power system. And here we have it. And then you see that there are separate interfaces, technical interface and market interfaces between the different elements of the system, just to keep the data privacy then for the systems. Good. Then let's go to the energy system of system, because this was the goal of this lecture. How we are going to go there. It is a process. The energy system of systems is the end situation of a process, and the process is energy system integration. That means we have to try to integrate the systems. What is should be understood under the energy systems integration? It is the process of operation and planning coordination of energy system across multiple pathways and geographical scales to deliver reliable, cost-effective energy services with minimal impact on the environment. It is categorized into three opportunities areas: streamline, synergize, and empower. What is streamline? It refers to improvement made within the existing energy system. That means we discussed that there are many energy systems. That is the electricity energy system, it is the gas system, there are cooling and heating systems, also the hydrogen, which do not have any, which are in construction, how to say. But also this energy system has to be developed themselves, have to be modernized before they are going in the process of the integration to create the energy system of systems. And for that reason, the streamline, it is very important, where there are necessary different institutional levers, policies, regulation, and also markets, because we discussed the structure market. It is not facilitating the integration of distributed renewable energy resources. Then we have the synergize, which describes the solutions that connect energy systems to create the energy system of systems. And this is the base in this case, the synergize. This should realize the connection of, or the coupling of, various vectors. So we discuss what is a vector for different energy systems. Within the second sector, for example, cross different vectors of the energy utilities such as electricity, heat, gas, etc. We cannot talk for a cross vector between electricity and hydrogen, because the vector of hydrogen, it is still under construction. And we talk in this case normally for cross-vector sector coupling. And then between another case, it is between the electricity and the end user to benefit efficiency and performance. The end-use sector coupling involves integrating different infrastructures within the customer plants, such as electricity or power, heat and cooling infrastructure, and modernizing energy demand while reinforcing the interaction between electricity supply and use, such as power to chemistry and so on. And the last one, it is the empowering. Empowering refers to energy system integration actions that includes the customer, whether through their investments, decisions, active participation, or decisions to shift energy modes, example, through energy communities. Because who is going to pay the bill for the energy transition? This is a big issue. And for that reason, this is a very important part of the energy transition, the empowering of the citizens for this one here, because we all has to cover the bills for the energy transitions, and this will be probably through the energy communities. And here we have what we discussed. It is presented here in a graphical mode. That means we have the energy system integration with the three opportunities. The first was the streamline, which is which includes the improvement within the vectors or the sectors themselves. Then we have the synergize, connecting the energy system, and the empowering. So when we are going to the sectors, we have the primary. So if you remember at the beginning of this lecture, we discussed for the primary sector, secondary, and tertiary sector, where the energy systems are sitting in the secondary, because there are classified the energy utilities, and here we have the heat, the electric, and gas. The link solution that we discussed now, it is the beginning on the electricity system. This link solution enables the sector coupling. That means the cross-vector sector coupling, but also the end-use sector coupling. And here we have the electricity in the middle. The vector, just keep in mind, there is the transport or the distribution of the electricity. There are the wires and the storage that we have there, and with heat, cooling, but also with gas. And then for the end users, we have the electricity, and the users are coming from different sectors. Can come from the electricity, from transports, for households, industry. That means this one here, agriculture, it is included in the first sector. Transport, it is a service, it is in the third sector, also household and industry itself. And this may be our link solution, because it is based in this fractal feature. It makes possible to realize the sector coupling. The other point is the empowering. That means are the energy communities, which are not in the focus of this lecture. So let's go. So we discussed the streamline. So let's go now to the sector coupling, because we would like to go to the system of systems. Here we have an overview of the three different systems. What do we have here? Just in the bottom here, we have the electricity networks and the electricity storage. You remember a vector, it is including the network, the grid, and the storage. And we have in the link solution three types of storage. One of them, there are category A, B, and C. In the category A are included the storages where the charging and discharging will be at the same point of the grid. For example, a normal battery, we are charging and discharging in the same point. Then we have the category B. For example, we have, in the case we would like to produce hydrogen or to produce synthetic gas. Then we have always with the surplus of the electricity. That means here we are connected in one point of the grid where the hydrogen will be produced, but probably or synthetic gas, but probably this one here will be used, let's say, in a gas power plant. That means the input will happen in another point of the grid. And the category C, it is load shaving. In the case, for example, that we can probably increase the water temperature here in this case, or we can decrease the temperature in a refrigerator from -16 to -24, for example. And this is from the electrical point of view is doing nothing else but the so-called load shaving. So we have the different category of storage in the link solution itself. They are defined. That means here we have the presentation of the vector of the electricity. On the left side, it is drawn the gas network and the gas storage, and all together are making the gas vector, are creating the gas vector. And on the right side, we have the cooling and heating system. And here we have the thermal networks, and heating and cooling storage or thermal storages are put together. That means here it is presenting the three vectors of these energy systems. And then there are processes which can create exactly the coupling or the integration between these energy systems. For example, we have here gas to heat, and probably you have heard about this one here. And this is a process, the process gas to heat, which can be realized with the hardware, which is the gas condensing boiler, for example. If we are going now to an electricity network, there is a lot of possibilities here to couple the electricity with the gas network. And here we have in bidirectional the possibility to couple these ones. One of the processes to couple the electricity with the gas network is the so-called power to gas. And in this case, this gas may be hydrogen. So the hardware may be an electrolyzer which produces the hydrogen, or it can be set up there also a methanation reactor, and then we can produce synthetic gas to reach this net zero energy strategy. And the process is power to gas. But we discussed that we can set up the electrolyzer, but there is no any vector for hydrogen. So we have to find the possibility to transport this one here with different transport vehicles. There is no pipes, there is no for hydrogen. And for that reason, we have put also here methanation. And this we have to discuss also what is the time horizon that we would like to realize this sector coupling, the system of systems. We have to wait until the whole infrastructure it is for hydrogen it is constructed, but also the end user has been changed, or we can go in the direction of synthetic gas and net zero, not directly to decarbonization, but to the defossilization of the energy. Then we have also the other part. So we have using the fuel cells we can produce under others, but we have also the gas turbines, for example, but they are not part directly of the coupling of the vectors themselves. It is a coupling of the end users. So here we have gas to power, and they are using, this is the process, and they are using the hardware in the structure, the fuel cells. And this can be used to couple gas and electricity network. And on the other side, we can go from the electricity and realizing the so-called load shaving, power to heat, for example, heat pump, it is the structure, it is the hardware to realize this process, and then we can storage electricity in a thermal type of the energy. From the point of view of the electricity grid is this load shaving. Over this one here we see the producers of the electricity. So here we have the renewable heat and cooling electricity, or electricity and heat system. This is combined power and heat, for example. And then we have renewable or synthetic gas and fuel, or there are gas and fuel produced by the renewable energy resources which have the name synthetic gas or synthetic fuels. That means in this case, using them we will reach a net zero economy or a net zero energy system. And then we have in the down we have the end users. which we also discussed before, that are households, and they are using electricity, gas, and heat and cooling, all this kind of the energy on themselves. The tertiary sector, the industry, agriculture, but also for the transport, we have the ground transport, maritime, and aviation, which are here the end users, which may be prosumers and consumers. And here in this form then so we are going in the direction of the integration, and when they are integration, we have then an energy system of systems. And if we can go here, and for a better understanding of the different vectors, what do we see in this picture? So we are familiar now with the fractal presentation of the power grid. So here we have the grid link, you remember? So we have the grid link with the secondary control and the interfaces. Then we have the producer link on the left side, the storage link on the right side. And here it is the generalized link-based architecture. That means here we have all voltage levels included on this one here. And in the producer link, we have all possible producing resources, so the all energies resources here, like hydro, wind, the conventional hydro, wind, solar, geothermal, bioenergy, waste heat, and so on. And then on the right side, which is the most important thing, it is we can realize the integration of energy systems through the element of the architecture, which is the storage element, the storage link element. With this element, we can put the architecture all together, because we have to think these are huge systems which are extended over one continent. That means we need the structure, this one here, and the linking or the coupling of these systems will be realized through the element of the storage. And here we have the electricity energy vector, which is including the grid and the energy and the storage. And then we have the other energy vectors, which may be the gas, for example, network, which is using the chemical energy, or heating and cooling network, which is using the thermal energy. But also here, it is also the hydrogen, when the vector it is constructed in 2050 probably. And then here are the processes: power to grid, power to heat and cooling. But in meantime, in the storage, there are also storages used locally, directly from the power grid, for example, where there is no any cross vector coupling, for example, power to wind, to water, pump water power plants, where it is used the potential energy to storage the energy. We have power to fly hills, which is used the kinetic energy. And we have power to battery, for example, which is using the chemical energy. In this case, there is no cross vector sector coupling, only in this part. On the last part of the picture, we see the end use sector coupling in the different sectors, in the transport, with industry, household, services, agriculture. And here it is taken one example for the households. And here we see the picture of the house itself. We have, you see here, the grid, the storage in form from cooling, heating in form from battery. Oh, sorry. Okay, from battery. And we have also of producer, where here we have the photovoltaic, which is producing electricity, but also solar panels, which are producing hot water. So they are for the producing of the hot water, and are used then for the heating of the houses themselves, and also the geothermal heat exchanger, just for combining this kind of a system. And the end users are here. That means the end use sector coupling happened normally within this sectors: the transport, industry, household services, and agriculture. Why the cross-vector sector coupling? It is happening in the grid level, in the vector level. And when these both are realized, then we can talk then for the system of systems. If we are just going in the example of the gas grid, if we are trying to have a overview of the gas grid, this is, for example, the producing wells, which are far away from the demand centers of the gas. Then there are some compressors there. There are transmission pipelines. Then we have underground storages, so with the old elements, so there are some city gates for regulators and meters, and here we have a terminal on LNGs, non LNGs. This is a case of the American Gas Association, because we would like to couple this system to create the energy system of systems. And if we are trying to see this one, here we have the transportation level with high pressure. Then we have the distribution level, medium and low voltage. So distribution has normally two pressure levels, medium and low pressure level, and also the customer level. And then we have to make the analogy, and because we want to bring them all together. And here it is the electricity grid. So here we have the transmission level, high voltage. Here we have high pressure. That means the high voltage and pressure, there are two analogy variables. Then we have here the distribution in power grid, in the electricity grid. Here we have in the gas grid medium pressure and medium voltage. Then we have low voltage and low pressure. And then we have also in the customer level, where there are the end users which are using electrical devices, but also then gas devices for cooking, and depending on different houses may use only electricity or gas and electricity, and so on. For example, in Italy, almost in all Italy, they are using both a lot of gas, electricity, and they have a restriction up to 3 kilowatt in the installation of the houses themselves. So how can we realize this one here? Then what we see here, and this is important, then when we derive the architecture, we have here once again the high voltage grid, the medium voltage grid, the low voltage grid. Here are the producer on this side. Here are the storages with different categories. So you see here with different colors, it is explained. What is the nice thing, it is that we have also within the house itself the same structure as in the different voltage levels, because this is the fractal features. And then they are connected. Okay, here we have the TSOs and the DSOs, which are operating these grids, and here we have the customer plants, and then here we have the energy communities which have the connection with the market. On the right side, we have the gas network, which is connected with coupled with the electricity grid through the coupling components. And then we have seen that the coupling components, for example, will be electrolyzer and the methanization reactor, as we discussed before. That means here it will be realized, and this is the storage, the element to realize the coupling, it is the storage. Then we will have the cross-vector sector coupling in this level, and here we will have the end user sector coupling, where we have to talk then also for the development, the streamline on the gas itself, also the development of the gas market, and then there are many issues has to be discussed then to go then deeper on this one. If we are thinking, okay, in Europe we have a very big deficit where we are importing more than 50% of the energy, and then if we are just treating the PV systems on roofs can cover already in use, making them very effective. That means people are if we would like to install photovoltaic, then we don't need to use other surface or the other resources, but because these here are the so-called brown areas. The large-scale implementation of the rooftop challenge, but it is challenges a lot the power grids themselves. Another motivation for the sector coupling, it is the huge possibility of storage that exists in the gas level. Here we have an overview of the storage capacity from 10 kilowatt hour. So it is the scala, it is logarithmic. On this part, it is the storage capacity, and the epsilon axis, we have the storage time. Then here we have, for example, with the flywheels, we can use the we can store about 10 to 100 kilowatt hours, and they can be used for 1 hour, not more. Then there are the batteries, and we see here that the largest existing storage capacities exist for the natural gas, for the methane. That means we have here a storage capacity on terawatt hours, thousands of terawatt hours, and they can be used for a long time then. And this is very important to cover the volatility of the renewable energy resources. And this is one of issue just to take care, and probably to work with synthetic gas probably has to be calculated, or we have to wait until the hydrogen vector it is constructed, the storage capacity, but the hydrogen itself, the existing infrastructure for methane cannot be used for the hydrogen. And this is the point. So the gas networks presents the largest storage capacity. The conventional power plants are needed to compensate for the volatility of renewable energies. That means if we have synthetic gas, that means we can reach the net zero. In the case we can, when we use the synthetic gas to operate the gas power plants, which are very important to balance the changing of the renewable energy resources. And here it is one scheme, for example, how can be realized exactly this process. You know that now the high voltage, medium voltage, low voltage grid, with the surplus of the energy which is produced, for example, for the wind park just in the North Sea and so on, can be produced with a P surplus. P is normally red for the active power. Through it is a category B of storage in the gas system, with the coupling component electrolyzer plus methanization reactor. It can produce the synthetic CH4, which will be injected into the gas grid, and then when it is needed, this synthetic gas may be used from the gas power plants to balance the renewable energy resources. And this can be done at each level, as you see here, in high voltage, medium voltage, low voltage, but also in the customer plant levels. And in the case we are realizing it, this one here, and coordinating this work, then we have realized the energy system of systems. Just to conclude, the future energy system in Europe will be a system of systems. The energy system of systems will enable the defossilization of the industry. The energy system of systems increases the flexibility of the power systems, because now when there is a surplus of the electricity, we don't know what to do, and we are cutting. We are switching off the photovoltaics in the case we cannot manage the electricity within the power grids. In this case, we're increasing the flexibility because we can produce gas and so on. So it's a very important point. A holistic approach is necessary for the integration of the energy systems, and link paradigm is an instrument to enable the energy system of systems. So thank you very much for your attention, and if you have questions, it will be a pleasure to answer.
Thank you very much. Thank you. Yeah, so we can start with the questions. So if there are questions in the audience, you can also type in the chat, or you can open your mic. Is there some questions in the audience in the lecture hall? We have some questions.
Can I see the question so I can switch off the slides? Or?
Okay. At the moment, there's no question, so I'll start with an icebreaker question. So maybe, thank you very much for explaining this link system, and you also told what is necessary to streamline the hardware. But in your opinion, what is necessary to streamline the system of systems? So it's also an information part of streamlining. What has to be done to transform our energy system as it's now, to transform it to what you explained in your presentation?
So in my opinion, it is for me the most important thing. It is establishing the architecture, because the system is very big. And what's happened nowadays, people are trying to solve to find a solution somehow. And it is possible that everybody is doing something. It can work locally, but it cannot work as a whole. For that reason, if we would like to go fast on the new era of the energy systems, we need a little bit time at the beginning to establish the architectures and to create sustainable developments for this one. So the fractality, it is one of the features that's used in the leak solution, and I believe that what it is the next step, it is developing or designing in a similar way with the fractal feature the architecture for the gas system, because we have to analyze, if you remember, the streamline. So what should be done also in the gas system itself, what kind of investments, then for example also the gas can flow in both directions, then we can integrate and couple them too. So for me, the most important is just it is establishing the architectures and in the parallel we has to be worked also for the development of the market, which is not that easy.
So yeah, I fully agree that gas will play a role in most importantly for storage. But what I don't agree is that in future we will have the gas boilers for heating anymore. So we use the gas for producing electricity plus heat, but not only for producing heat. That was in your graph, I think.
No, I just gave only one example. It can be the same because it is the time was very short. It is not only gas. Also from the point of view of the gas, it should be studied. Because if we would like to have an impact on the climate change, we should act very fast. And now we should go from the status quo now directly to the decarbonized with hydrogen, for example, or we have to go through the net zero and then decarbonize, defossilization and then decarbonize. This has to be studied really, because I believe that it will take much longer time to realize the decarbonization than to go first to the defossilization and then to the decarbonization. So, but we need project. So it is needed the calculation, really a systematic calculation, also economically, that what is the way, because we have the trilemma in our. So we have to create a system which it is sustainable, Then we have it should be economical, and also from the technical point of view should work. And to put all these three together, it is not easy. That means what to do, for example. It makes sense, but we have to change the objective functions of our optimization routines in all, because it makes sense to destroy, for example, the gas structure, infrastructure, and to build the new one. But we have to calculate the CO2 production and then the CO2 production and so on, or to use as far as possible the existing infrastructure by going to the net zero, and then in parallel, to construct for example, the hydrogen infrastructure. The vector of hydrogen do not exist. This is reality.
Yeah, you're right. That's true. Any other question? So you can see here in the yeah. So I think we ran out of time. So I think we have to come to an end. So thank you very much for coming, and yeah, for your lecture. So yeah, maybe use your slides also. Could you provide them
Yes,
for
of
the
course, of
students?
course. I can
Thank you
send you
very
the
much.
slides. It's no problem at all. Just you can
Thank you.
publish them. This is.
Thank you very much. Okay. Yeah. So if you have no other questions, thank you very much again. And yeah, hope to see you in person in Innsbruck sometime. So then we can talk
It will be
more
a
in
pleasure
detail.
just to sit together or to discuss more in detail, many things that are there. And I am so sorry for the inconvenience at the beginning that the technique it didn't work somehow.
No problem. Yeah, thank you very much. Okay. Yeah, then thank you again. And yeah,
Thank you.
see you next
Bye.
time. Thank
Thank
you.
you for the
Goodbye.
invitation.
Yeah.
Bye.
Thank you.